Welcome to the deep dive. Today we're diving headfirst into something really ingenious, something nature figured out that allows life, well, life itself to happen. We're talking about how certain reactions, ones that look impossible on paper, reactions needing a huge energy boost, how they actually manage to happen efficiently inside every living cell. I mean, think about it. Our bodies are constantly building these incredibly complex molecules, proteins, DNA, doing complex things like moving muscles. Energetically, it's all uphill. It needs energy. So how does life pull this off? How does it build order when thermodynamics seems to say no? So our mission today is a deep dive into reaction coupling and these key players called activated carriers. We've looked at sources covering everything from Gibbs Free Energy to Hess's law. Get ready for some aha moments about nature's clever energy tricks. Okay, let's unpack this.
It really is a fascinating question, isn't it? And the challenge is very real. Many essential processes are, well, energetically unfavorable. They need energy input. But like you said, the sources show some truly elegant solutions. What's really fascinating, I think, is digging into how energy is managed, how it's transferred in these systems. It's fundamental.
Absolutely. So let's get our footing here. Spontaneous reactions in chemistry. It doesn't mean fast, right? It's about energy. We talk about Gibbs Free Energy. For anyone listening, what's the key thing to grasp about a negative U? What does it signal?
Right, that's a crucial point. A negative U-mu means the reaction is exergonic. It inherently releases free energy. It means the system moves from a higher energy state to a lower, more stable one. Think of a ball rolling downhill. It can do work naturally. So negative U-mu means the reaction can proceed on its own. No continuous energy push needed. It's energetically favorable. That's the basic rule for reactions that just happen.
Okay, downhill. Releases energy, negative U. Got it. But then the big question, what are the uphill ones? Positive U, the ones that need energy, building proteins, DNA. These need serious energy. So how do cells do it? This is where, it gets really interesting. Our sources talk about reaction coupling. How does that work? How does one reaction fuel another?
This is really where the cell's cleverness comes in. Reaction coupling is a powerful strategy. Imagine two reactions. One favorable, releasing energy, negative U.
The downhill one.
Exactly. And another unfavorable, needing energy, positive U. The uphill one, if you link these, couple them into one process, you can sum their individual U values. And here's the crucial part. If the energy released by the favorable one is more than the energy needed by the unfavorable one,
then the total is negative.
Precisely. The net E for the whole coupled system becomes negative. And that means the combined process is now spontaneous. It's not magic, it's just clever energy bookkeeping. The favorable reaction essentially pays the energy cost for the unfavorable one, like using energy from water flowing downhill to pump some water back uphill. Without this, building the complex molecules of life just wouldn't happen. It's fundamental.
That makes so much sense, like an energy transfer. Okay, and speaking of summing things up, Hess's law comes up in our sources too. How does that fit in? What is Hess's law telling us here?
Hess's law. It provides the solid thermodynamic ground for summing these energy changes. Simply put, it states that the total enthalpy change for a reaction doesn't depend on the path taken. One step, many steps. The overall enthalpy change is the same.
Okay, so the start and end points determine the energy change, not the journey itself.
Exactly. And while Hess's law is strictly about enthalpy, the principle applies broadly to Gibbs Free Energy, too. The total AG between reactants and products is constant, no matter the intermediates. Why this matters for coupling is huge. It confirms we can treat these linked reactions as a single system and just add up their AGs. We focus on the overall change, the start and the end. It validates the whole approach and lets cells manage these complex pathways predictably.
Right, so the theory holds up. Coupling happens. The energy math works out because the past doesn't change the overall energy budget. But how? How do these reactions actually connect on a molecular level? It's got to be more than just numbers on a page. The sources mention activated carriers. These are the molecules, enzymes used to link reactions. What are these things? What's special about them?
Yes, exactly. There's real molecular machinery involved. Activated carriers are just that, carriers. Specialized molecules that shuttle energy or chemical groups around the cell. Think of them as tiny rechargeable batteries or delivery trucks. Their key feature, they have what's called a high energy bond, often at one end. This bond holds a significant amount of chemical potential energy, like a compressed spring.
A loaded spring.
Right. And when that bond is broken, usually with the help of an enzyme, that energy is released in a controlled way. Enzymes are the facilitators here. They physically bring the carrier together with the molecules, the unfavorable reaction. They ensure the energy released from breaking the carrier's bond is immediately used to drive the unfavorable reaction forward. It's a direct handoff, very efficient, no wasted energy just floating off as heat.
Little molecular springs.
Yeah.
Ready to pop. That's a great image. And you mentioned high energy bond at one end.
Yeah.
Okay. So are there famous examples? The sources mentioned a really common one.
Oh, absolutely. The undisputed champion, the universal energy currency in virtually all cells is ATP, adenosine triphosphate.
ATP. Heard of it.
If a reaction needs energy, odds are ATP is involved. Its power comes from the bonds linking its phosphate groups. Breaking off the last phosphate releases a good chunk of usable energy. It powers almost everything, building molecules, muscle contraction, nerve signals, you name it. Fun fact, you probably recycle your body weight in ATP every single day. That gives you an idea of the sheer scale of this energy management.
Wow. My body weight in ATP. That's incredible.
It really is. But ATP, while central, isn't alone. There are other important activated carriers, often with more specialized roles. Our sources mention NADH and NADPH.
Right. NADH and NADPH. What do they do?
They are primarily electron carriers. They shuttle high-energy electrons. NADH is key in breaking down food for energy, think catabolism. It carries electrons ultimately used to make more ATP. NADPH, on the other hand, usually provides electrons for building things, think enablism, like making fatty acids or protecting cells from damage. Different jobs, different specialized carriers.
Okay, so ATP for general energy, NADH and NADPH for electrons.
Yeah.
Any others?
Yes, acetyl-CoA is another big one. It carries acetyl groups, which are 2 carbon units. It's crucial in linking carbohydrate and fat breakdown to the main energy-producing cycle in the cell, the citric acid cycle. And it supplies building blocks, too. And there's also GTP, guanosine triphosphate, structurally like ATP, but used in more specific roles, like in cell signaling and making proteins. So you see this diversity, right? It raises the question of why so many. It boils down to efficiency and specificity. Different reactions need different kinds of energy packets or chemical groups. Nature evolves specific tools for specific tasks, all using this core principle of coupling energy release to energy need. Understanding these molecules really brings the whole concept to life.
What an amazing system. So let's recap. We saw that negative Ig means a reaction can go on its own, releasing energy. Then reacted coupling this brilliant trick where an energy-releasing reaction pays for an energy-requiring one, making the impossible possible. Underpinned by Hess's law, telling us the overall energy change is fixed regardless of the steps and the actual molecular players. These activated carriers, ATP, NADH, acetyl-CoA, GTP, acting like energy shuttles with their high-energy bonds, orchestrated by enzymes.
Precisely.
It really is an elegant solution to a fundamental problem. Without it, life as we know it just couldn't build complexity. So for you listening, it means these incredibly complex processes like building you are all based on these manageable energy-coupled steps, a constant, intricate dance of energy transfer.
Indeed. And thinking about this incredible efficiency, it does leave you with a question, doesn't it? Given how nature overcomes these energetic hurdles with coupling and carriers, what other seemingly impossible challenges, perhaps outside of biology, could be tackled if we found the right activated carrier or the right reaction partner? Think about it. Where else could we strategically link an energy-releasing process to drive a needed but difficult outcome? In technology, engineering, even in how we organize efforts. Where can we find the exergonic to power the endergonic?
That's a really powerful thought to end on, taking these biochemical principles and seeing where else they might apply. Fantastic. Well, thank you for joining us on this deep dive into energetic reactions. We hope it sparked some curiosity. Until next time, stay curious.